Hello, my name is Drew Sheriff, and I'm going to be going through Lab 2 today. So the purpose of this lab was to demonstrate Newton's second law and the momentum principle. The momentum principle is force is equal to the change in momentum over time, and Newton's second law is equal to F equals ma. So the models that were used were, if you see on the left, that's tracker. So in the video, as you can see, I have my hand out and I dropped the paper ball, and using tracker I can record the position, time, and get the velocity and such. And then on the right, I simulated this in GlowScript with the position over time graph you see. And yeah, it's about the details of the experiment. The assumptions that were made was, at first, there was no drag force being accounted for, and then we assumed that it was equal to negative b times v squared, and that was assumed to be the drag force present in this experiment. The main fundamental principles are the velocity change formula, which is the top one, the position change formula, weight is equal to mass times gravity, the magnitude of the drag force is equal to v times v squared, and the net force for this experiment was the force of gravity, W, plus force of drag force. A brief preview of the main result. Newton's second law and the momentum principle proven to be true. This is the graph of the results, the experimental model, and model with drag. The system is the paper ball. The surroundings are everything but the paper ball, so the ground, me, etc. The initial conditions were that the drag force was equal to 0. That the force is equal to weight plus drag force, but since the drag force is equal to 0, it's just the force of gravity. The paper ball is not yet moving, and time is 0 at the start. The coding details explained in a clear logical manner. So basically, if you look at the first arrow, we set b equal to 0.0017 because it was given to us as that. And then the next arrow is the time of the experiment. So when time is less than 0.4, these conditions apply, and 0.4 was when the ball hit the ground. So I made that the last time that it would go to. And then for the net force, there we got weight force equal to negative mass times gravity times j hat, which basically just means it's going to be going downwards towards the ground. mg towards the ground. The drag force is equal to b times the magnitude of the velocity squared, because we cannot square a vector, but the magnitude is scalar, so that works. The net force is just W plus drag force. And then, of course, we have the velocity change formula and the position change formula. And the similarities and differences between the data and model predictions were that with the model, it was assumed that it would go, it would hit the ground sooner, and it would, because it's not accounting for drag. But with model with drag, it was a little bit closer to being accurate. It assumed that it wouldn't get there as fast, but it wasn't as close as the experimental, which took the longest to hit the ground. Potential sources of error are in plotting the ball's mass points, video camera slight movements, and in plotting the scale. What does it mean? Terminal velocity. The model with drag predicts it because at a certain point, the drag force will equal the weight force. And then net force will be 0 with terminal velocity because there is no acceleration. And if it was thrown down with initial velocity, it would still end up with the same terminal velocity because the drag force is proportional to velocity squared. So at some velocity point, the forces will cancel out, and that is the terminal velocity. And as we see with that graph at the bottom, it's flattening out, and it'll eventually just a horizontal line, which indicates it ended.